Polar functions, a quick review published by A Squared. The domain of polar functions is 0 to 2 pi for all polar functions except for odd petal roses, which is 0 to pi. And to find the intersection points, you want to set your polar curves equal to each other and use algebra and inverse trig to find the correct theta, just like finding intersection points between two rectangular functions. To find the area, we use this formula that's displayed on the screen. And usually to find the area between two polar curves, you want to take the outermost function minus the innermost function. And dy dx is a form of slope, as you know, and it gives us slope of the polar curve, but it's in rectangular form. So you have to obtain dr d theta from the derivative of the polar curve, and using x equals r cosine theta and y equals r sine theta, dy dx can be found. So if you take the derivative of x in respect to theta, and you take y in the derivative respect to theta, then you can find dy dx. And this can be, in order to find those derivatives, you have to use chain rule and product rule, or you can memorize the formula that we have on screen. So in order to use these, just make sure you plug in r and dr d theta in order to get your dy dx.
Now we're talking about tangents at the poles, so this is pretty simple. First, we have to set r equal to theta, and then using algebra and inverse trig, we must solve for theta, but we have to make sure to solve for theta in the entire domain, which is given in topic 1. Now we have to take the tangent of each theta and write the equation of the tangent line. For example, if the tangent of theta is 1, our coefficient in front of x is 1 and y equals x. Next, we're going to talk about other tangent lines in general. This is very similar to tangents at the pole. However, we have to set the two r equals equations equal to each other. We have to solve for theta using algebra and inverse trig, and then we have to take the tangent of each theta and write the equations just as we did before. Next, moving on to asymptotes. As stated earlier, dy dx is actually dy over d theta over dx over d theta. We usually write dy dx just because the thetas cancel out. And horizontal asymptotes is when the numerator, aka dy d theta, equals 0. So we set this value equal to 0 and solve for all, if any, theta values. Vertical asymptotes is when the denominator, or dx d theta, equals 0, and we set this equal to 0 and solve for all, if any, theta values. Finally, we're going to talk about arc length and surface area. Arc length is the perimeter. So first, we solve for dr d theta, and then we plug into the formula below from alpha to beta, the square root of r squared plus r prime squared d theta. And now for surface area, we can do surface area around the x-axis or the y-axis. Around x, we have y times arc length, and around y, we have x times arc length. Thanks for watching.